So we're going to move away from our friend the metric that we have been getting acquainted with and enjoying, and starting today, or starting with this lecture, I want to talk a little bit about classification, and even more so risk prediction, and things we can say about fairness when we don't necessarily have a metric or a fully specified metric. So we're going to be in the setting of trying to predict individual probabilities. Okay, that's what we call prediction, risk scores. So it is often the case in kind of automated classification and prediction that we're trying to predict things like, what's the probability that a patient, the doctor's wants to know what's the probability that a given patient will have a major cardiovascular event, a heart attack, in the next 10 years. Or a judge would like to know what is the probability that a defendant will recidivate, will commit a crime if they get released on bail. And a loan officer would like to know, what's the probability that this individual is going to pay back a loan if they are given one. So these are excellent questions, and I think, I wish we had answers, but of course, as Cynthia said, going back to yesterday, these are non-repeatable events. Either the person will have a heart attack or not. What exactly are we talking about when we say probabilities? And it's an age-old question in statistics. I don't have a fully complete answer to the debate about probabilities, but we'll have things to say about it as we talk today. And I think, one thing is, this thing about, or this point about individual probabilities, may make us a little bit squeamish when we think about it mathematically. What's the probability space? What are we really talking about? Really good questions. The problem is that I think this goal of trying to predict the probability that a person will have a heart attack, that's not going away, I think. Doctors, need to know answers to these kinds of questions. So, we need to have some understanding of what can we say, and hopefully we'll develop such an understanding today and tomorrow, one such understanding over the lectures. Okay, so to ground things, I want to talk about this question of predicting probabilities in two settings. One is the batch setting, which hopefully we've started to know and love over the last couple of lectures. And the other is going to be the online setting that we won't, well, I do want to say something about it. So I want to introduce it, I want you to know about it, but it won't be our focus. Okay, so in general, for the problem, in both settings, our setup is going to be similar to what we talked about yesterday. So we'll have some feature universe, some universe of people with their features. So every person is a member of this universe, large X, okay, including all of that person's features. And I want to talk about trying to do risk prediction when we have binary labels. Okay, so the labels are going to be either 0 or 1. Either, the person will have a heart attack or they won't have a heart attack. They will return the loan or they won't return the loan. And then we have two settings to talk about. What we've talked about so far is the batch setting, where we assume that there is some fixed, true, underlying distribution on the labeled examples. Okay, there is really some underlying probability distribution over labeled examples. XY. We don't know, so it's an unknown distribution. We don't know what the distribution is, but we can observe samples from it. And we can assume that the samples we have observed are drawn from the same distribution. The samples we've observed in the past are drawn from the same distribution as the new examples that we're going to see in the future. Okay, so that's the batch setting. And why is it called the batch setting? Because we can build a learning algorithm that gets a training set, a batch of labeled examples So collection of historical people. Did they return the loan? Did they not return the loan? Did they have a heart attack? Did they not have a heart attack? And then we use that to try to predict for the future, for unseen examples. So we get our training set of xi's and yi's. And the goal is to output a predictor that will map new instances to what we hope. I won't say we hope that they are the correct probabilities. I will say that we hope that they are meaningful probabilities. Okay? So what do we want? What are we after? We want to estimate. So ideally, or our motivation, which may be out of reach, but that's what we would want, is to approximate the correct probability. So the probability for a given x over this underlying distribution, the probability that their label is 1. Okay, so ideally for an individual little x, we want to know the conditional probability for, given that these are the person's features, that their label will be 1. And this is sort of the truth. This is what we think of as the truth, and we'll call it P star. Star because it's special. P star. That's the correct probability, the true probability, of this person returning the loan, having a heart attack, etc. And, I don't want to harp too much on this, even though I think it's like as Cynthia said, the foundational question of data science. The defining question. A defining question. It's a definitional, it's a definitional and defining question for the field. What is the meaning of these probabilities? And what I mean by that is these probabilities are not knowable. This P star is not something we can get our hands on. We see person X, either they return the loan or they didn't return the loan. I have no idea, I don't see the alternative universe in which, maybe there's randomness over whatever, the weather and, the economy and the position of all the, all the electrons in the universe. What's the alternative universe in which they didn't return the loan? What's the probability? We don't get to see that. We don't have access to this P star. All we get to see is one draw, right? Or a few draws. For this X, for that X, did they return the loan or did they not return the loan? Nonetheless, we try to approximate this P star in a meaningful way. Often in machine learning, the paradigm is we define some loss function between our predictions. I'm actually going to try to call, looking ahead to tomorrow, I'm going to try to call our predictor that we output P tilde. Okay, so that's what the learning algorithm, that's our approximation for the truth, P star. And we want to output meaningful predictions, so often, one paradigm in machine learning, loss minimization, is try to minimize some loss. Of course, I just want to say it, we all understand it, but nonetheless, I will say it. Yesterday, we talked about classification, where we're trying to output a label, either 0 or 1. Today, we're talking about outputting a probability, trying to estimate the probability of being 1. And then we try to minimize some loss of P star. So, maybe I want to minimize the distance between P tilde and P star, my approximation and the truth, but I don't know what the distance is because I don't know what P star is. So I want to try to minimize something that I can measure, and we can minimize all sorts of loss functions. For example, the L2 loss, that's the expectation over X and Y of the difference between P tilde of X and the label Y squared. Okay, that's something we can try to minimize. So that's the kind of one very popular paradigm for batch learning, for the batch setting in machine learning, and we'll talk about other paradigms today and tomorrow. So does that all make sense? Good. So now that we remember what the batch setting is, I want to define the online setting, talk about it briefly, and then we will spend more time actually talking about fairness of the predictor in the batch setting. maybe I'll already say, looking ahead, I haven't mentioned fairness so far at all. Looking ahead, I'll repeat it, but I do want to say, if we're doing loss minimization, if we're trying to just kind of minimize this loss, and notice, we don't expect to bring it to 0. Okay, so we don't expect to approach P star. Even P star itself doesn't necessarily. P star does minimize this loss, so that's a fact you can prove, that the thing that will minimize the squared loss is if you output the correct probabilities. But if P star could be, and this is part of the defining question, maybe P star is deterministic. Everyone has a label, 0 or 1. Or maybe there is some probability, we don't know. If P star is deterministic, then you can bring this to 0. If there really is some probability, you can never bring it to 0. And in general, we don't know how close are we, given our approximation P tilde, how close are we to the optimum that P star would achieve? We don't know the answer. We have some errors. And when we're thinking about fairness, there are lots of good questions to think about in this setting, right? Like, where does the data come from? Who chose the features? Where does the data come from? Are the labels fair? Are they biased? And there's also a question of, now that we have a predictor, and the predictor is imperfect, it will make errors. It's not going to be the perfect P star. Who's paying for these errors? Who is the predictor erring on? Is it more accurate on one population than on another population? And this is the type of question that we'll be concerned with for fairness. Okay. So anyway, that's a sneak peek looking ahead. So I want, in contrast to the batch setting, to define the online setting. We'll do that here. It's another popular so just ask, who knows this, like the machine learning in the online setting, who has seen this before? Okay, so not so many. So this is trying to get away from the assumption. So often we think about, when we talk about predicting the probabilities of events, one example that's being given is the weather. What's the probability that it's going to rain? That it's going to rain today, and one setting you might think about is the batch setting, but maybe the tomorrow's weather really doesn't have much to do with today's weather or yesterday's weather. So we're sort of in a setting where we don't have a static distribution that we can learn on and then deploy our predictor, but rather things are changing dynamically. So how do we capture that? I'm going to show one formalization. This is known as the online setting with contexts. So we have rounds. Think of these as days when we're doing weather prediction. And so we have rounds going from 1 until some number n. Everything will be finite today, although people do talk about infinite time horizons as well in this setting. And try to think about what happens at the limit, but not today, not for us. So in each round, we get some context. Xi. Okay, think of this, if we're doing weather prediction, this is sort of meteorological measurements that are relevant for the day, or if we're doing, again, the example of a loan, granting, the probability that a person will return a loan, maybe it's some relevant features. So this is sort of the equivalent of the features in the batch setting. Then we try to predict the probability that it will rain. Okay? So we try to predict the probability that the Boolean outcome that we will observe in this round is going to be 1. Okay? So this I'm going to call, so really what we are doing here is we are computing some mapping. Given the context, for any context we might see, our algorithm needs to determine what is its estimate of the probability of rain. Okay, the probability of yi equals 1. So really we have here a predictor, let's call it P tilde for round I. That's mapping, So we need to output our prediction. We're going to allow, and we need to allow, it's important, probabilistic prediction. So actually we'll have a distribution over probabilities. Okay, so distribution over a predicted probability of rain between 0 and 1. And really I'm thinking about this predictor as a mapping. For any context that I might be given, the algorithm is telling me a strategy that it's going to play. I'm hinting ahead that you can see this as sort of like a game between nature and the person, the forecaster, the forecasting algorithm that is predicting probabilities. So that's sort of the output of the algorithm, and then we observe whether it will rain or not. So an outcome in 0, 1, and we pay some loss. Okay, maybe something like the squared loss, maybe something else. So some loss depending on our prediction and the actual observed outcome. So if we predicted a small probability of rain and it rained, we have a high loss. If we predicted, a high probability of rain and it actually rained, the loss will be small. So one thing that's sort of mind-boggling here is that there's no assumption about how this yi and round I is connected to what we've seen before. Okay, so might be completely unrelated. And still we want to do well, and we'll talk in a minute about that. I mean, it's really important to understand what we mean when we say to do well. But that's the big difference between the online setting and the batch setting. In the batch setting, there's some sort of method to the madness, right? There's a fixed distribution, we get to see samples from it, and we are tested on our performance on this distribution in the future. In the online setting, there's no distribution, things change dynamically, and still we're trying to do something meaningful. Questions? Okay, so, yes? So it's very, very non-Bayesian, right? There's no assumption here. There's no prior. Everything is just like, completely adversarial and completely sort of might be unpredictable. We'll see in a minute that we can hope to do some things, but there's definitely no Bayesian assumption here. So what can we hope to do? When I say that we want to do well, any suggestions for what we might hope to do? Yeah, minimize regret. So I'm gonna just call that being competitive. So try to compete. With a fixed class of predictors. So maybe I can't guarantee anything. Maybe things are maybe it's total madness. Maybe whether it rains or not is just a coin flip every day. And then no one can predict it. Certainly I can't. And that's okay. So all I want to do is to be competitive with a fixed class to do as well as any predictor, any forecaster in a fixed class H. Okay, or nearly as well. Okay, so I want my loss over many rounds to sort of approach the best loss in a fixed class of predictors, H. And this is the setting of regret minimization or online learning. There are many beautiful algorithms. One really nice algorithm, there's essentially the algorithms give weights, or they sort of, you look at which experts, these are usually called, they're sometimes called experts, you look historically at which of your experts have done well, and then you give, you assign those higher weight and when you're making your next prediction. Okay, so you sort of have some distribution in mind over all of the possible experts or the predictors you're trying to compete with, and you give higher weight to the predictions made by the ones that have performed well in the past, but you randomize. Okay? And that ends up performing pretty well. There are a couple of different ways of doing this, but that's the general paradigm. Okay. Good, so we can do that. That's similar to what we talked about with agnostic learning yesterday, but in an online setting. There are algorithms. I won't talk about them at all, but it's a beautiful area of research, and I encourage you, if you're intrigued, to look at it and learn more about it. Okay, anything else that makes sense? So yeah, so this is sort of a relative notion, like, right, I want to do as well as this fixed class H. But, what about just, checking that my probabilities make sense, that they're reasonable? So for example, if I always predict a probability of 1 of rain, and it never rains, then I'm doing very poorly, right? My predictions make no sense. What I would want, and this is going back, we've talked about, properties like calibration, is I would want that, in days when I predicted a 30% chance of rain, 30% of the time it actually rained. That would be very nice. So we can design these tests where they're sort of sanity checks. And what I want is predictions that pass, at least basic sanity checks and hopefully sophisticated ones as well. Okay, so yeah, I want to formalize that. So that's sort of the focus of the forecast testing literature. So yeah, forecast testing. What we want are probabilities that pass sort of common sense, reasonable tests. So our predictions should sort of pass reasonable tests. Okay, what in the world is a reasonable test? So when I tell you that the test, for example, if we want to look at the probabilities and we don't want it to be the case that, we always predicted probability 1 of rain and it never rained, everyone nods along and says, yes, that seems very reasonable. And when I say that in the rounds where we predict a 40% chance of rain, 40% of the time, roughly, we want it to have rained, also you all nodded along and said, that seems very reasonable to want. So any other suggestions, or what is it that makes these tests sort of reasonable? So I think what makes them reasonable is that if we were right, if what we're giving are really the true probabilities, then they would pass these tests. Right? That's a very basic property we want from a test that makes sense. If we are giving the correct probabilities, if really, yi is being governed by the probability that we output in each round, then these probabilities should pass the test. Okay? That's a basic requirement we want from a test, and that's true. So for example, if really the test that checks that in the rounds where we said it will rain with probability 1, it almost always rained, or it always rained. If really the probability was 1, then we would pass the test. The fact that we're not passing the test means that we are not giving the correct probabilities. Okay, so it's sort of that kind of one-directional guarantee. If we were giving the correct probabilities, we would pass the test. So if we are not passing the test, we know that these are not the correct probabilities. Okay, so that's a definition of a test. So what is the test? Okay, so let's call it T. And the test gets the entire history. Okay, so it gets the context that we had, and the prediction that we made, and the actual outcome in 0 or 1. And we get n of those, 1 for each day. And then the test looks at everything that happens and decides whether to accept or reject the output 0 or 1. Yep?
So just going back to how you described a reasonable test, when you gave 100% or 30% as examples, are those point estimates the entire test, or is it implicit in the definition that you pass the test across the whole range of predictions you made? Because if you sometimes predict a 30% chance of rain and you sometimes predict 100% chance of rain, but actually it just rained all the time, then you would pass the test for your 100% predictions, but not 30%.
Yeah, so the test, so I'm not sure I totally follow, but let's just look at what that would mean for the test. So the 30% test would look at the whole history. It would focus just on the rounds where the prediction was 0.3, say these are in deciles, and it would check that within those rounds, 30% of the time, roughly, up to some error, 30% of the time the outcome was 1, and 70% of the time, roughly, the outcome was 0. And if that's the case, the test outputs 1, otherwise it outputs 0. It accepts or otherwise it rejects. Okay? So if I am outputting the correct probabilities, then really, when I'm saying 0.3, it should be the case that the probability of a 1 is 0.3, and this test will be passed with high probability by a Chernoff bound. Okay, so that's a test, and we say, so this is my computer science terminology, I say that it's epsilon complete. If it's true that always, if the probabilities are correct, then with high probability the test will be passed. So for every sequence of x1 context, x1 up to xn, and true probabilities p star 1 up to p star n, the probability that the test accepts, and let's talk, so the probability is over the draws of the yi's, the actual outcomes, which are governed here by p star I. The probability that the test accepts is at least 1 minus epsilon. So there can be some small probability of failure, right? If we're always, if it's always true that the probability of rain is 30%, but we happen to be really unlucky in terms of the outcomes, we might get a lot of rainy days and the test will reject, but that's sort of a vanishing probability. Okay, so we allow a small error probability, but really we want this to be close to 1. Yeah. So it doesn't, when we're actually running, it doesn't. But what I'm saying is that if I gave it the correct probabilities, it would accept. Okay? And if the test is not going to accept the correct probabilities, I don't know, what is it doing, right? Like we're trying to make sense of the probabilities. If someone comes down, from wherever they're coming from, and they give us the correct probabilities, we should accept them, we should be happy. So that's the condition that's written out here. I think formally, in the forecast testing literature, they say that the test does not reject the truth, except with probability epsilon, and the epsilon completeness is my theoretical computer science terminology. Cynthia, would you like to share with the class? I'm sure you have something. Good, so let's talk about some natural and important tests. Yeah, good question. So I don't have a soundness requirement, and yeah, somehow, what would we want our soundness requirement to say? Ideally, I would want, so you're definitely onto something. So ideally, I would want to say that someone who just has no idea what they're talking about and has no idea what the true probabilities are, they won't be able to pass the test. That would be great. And we're going to see that such a statement is completely fundamentally impossible. Like such a property is fundamentally impossible to achieve. So I would love to have soundness, but unfortunately, we can't get it here. And kind of a note for those in the audience who like computational complexity or cryptography, I will note that maybe we could hope to have some notion of computational soundness. Maybe if we restrict the running time of the forecaster to be small or polynomial, then there are settings where they cannot pass the test. We'll get to it. Okay, so I just want to talk about some natural tests, which will come up for us also in the batch setting. I want to talk about them here in the online setting. Okay, so one test that I want to talk about that's very basic is what we call the accuracy of the expectation. So ideally what I would want is that when I look at the average probability that was given over all n rounds, so I'm given my p tildes, the estimate, the forecaster's estimate for the truth, and I would want the average probability to, resemble the true, average probability of the outcome being 1. So the average of the yi's. So maybe up to some alpha additive fractional error. Yep. This color or the red? The red to something else. Sure, yeah. What? Any suggestions? Who wants to? Yeah, let's see what we have here. I have kind of like a dark, let's try, this looks like a lovely color. So let's try it, and if you can't see it, let me know. Okay. So good. So this is one basic property, right? Like if the average probability that I predict rain is 70%, I want it to have rained, maybe sometimes I predict 0, sometimes I predict 1, sometimes I predict 0.5, but on average I want it to be sort of correlated with the actual fraction of rainy days. Okay? So of course, this makes a lot of sense, and it's complete, right? If I'm giving the correct probability, then again, a Chernoff bound, the sum over n rounds, should be close to the correct expected outcome, the correct fraction of outcomes that was 1, right? Every round is sort of a Bernoulli. If every round really is a Bernoulli with probability p tilde, then the sum of these Bernoullis should approach the sum of the expectations. Is there a question in the back? Okay, so that's one test that makes a lot of sense. Is this any better, or is it still, you're sitting way up front, so if you're not seeing it, then, okay, let's try the, oh, maybe it's a matter of glare? Oh, angling in this, like this? Yeah, okay. Okay, good. Maybe it's a matter of the curtain, I don't know. But it's nice to have light, so, okay. Anyway, so that's a very relaxed test. We could be a little bit more demanding, and we could require a calibration, which we've sort of, no, unfortunately, we can't require a calibration. So I don't want to give a super formal definition. We'll do that tomorrow for calibration. But still, I want to think of these predictions as being discretized. Okay, maybe they're sort of deciles, like probability 0, 0.1, 0.2. Maybe there's some finer discretization. But for every possible prediction, so let's say these are integer multiples of 1 over m, so maybe m equals 10, or maybe it's kind of like a finer precision. So for every possible predicted probability of rain, of the rounds where I predict that probability, v, about a v fraction should have outcome equal to 1. Okay. So now the sum over the rounds I, where we predicted v, the value v, of the yi's, should be roughly v, I guess, times their number. So suppose there are S such round, or S of V, N of V such rounds. Then we want about a V fraction of them to have outcome 1. Okay, so which of these properties is stronger? Don't be shy. Calibration, right? Calibration, if we're calibrated, if for every one of our predictions our expectation was more or less correct, then the sum over all rounds, certainly the expectation will be more or less correct. Okay? But the other direction doesn't follow, right? Like it could be that in half the rounds I predicted 0 and it rained, and in the other half I predicted 1 and it didn't rain, and my expectation is a half, which is correct. Half the days it rained and half it didn't, but I sort of got it completely wrong. Okay, so calibration is stronger than accuracy of expectation. This is sort of like a minimal requirement. Calibration is a stronger one, still not super strong. So, any other suggestions? Is that it?
I can think of generalization of calibration, where you take subsets of large enough size. And the first example, just with subsets of large enough size.
Great. So, yeah, we can check calibration. What about checking calibration on the weekends? Did I predict, are my forecasts on the weekends calibrated? Are my forecasts in December calibrated? Are my forecasts on members of a minority group calibrated? Right, so we could certainly restrict ourselves to subsets. Looking ahead, I'll say we can't hope to be calibrated ex post on every subset because, ex post, I can look at the rounds where I predicted a half, and of those, maybe half of them rained and half of them didn't, but on the subset where it didn't rain, I won't be calibrated. So we want to define a set a priori, and then we can ask for calibration on the set. That's excellent. I think, so any other suggestions for tests that make sense? So I think a meta theorem that we will see tomorrow, in a sense, will tell us that there are no other tests that make sense. That every test that makes sense can be expressed as a kind of calibration test. So we'll get to that tomorrow. Okay. So those are the kinds of tests that we want to answer or that we want to satisfy for our predictions. And again, this is it's not a competitive guarantee. I'm not trying to compete with some external class H. This is sort of a qualitative guarantee about my predictions that I want to have, and it makes perfect sense to require it, even in this online setting where, we don't know what process is governing the creation of outcomes. So it's a good property to have if you can get it, but can we get it? I mean, if there's no rhyme or reason to the whys, can we actually have our forecasts be calibrated? Is it possible to get calibrated forecasts? What do we think? Okay, so I guess who knows, right? It's maybe not a great question because who knows? But yes, so it is possible to always get your forecasts to be calibrated. This was shown by Foster and Vora. And in fact, there's a much more, depending on your perspective, either powerful or depressing result due to Sandroni that essentially says no matter what the test is, there exists so long as it's a test that makes sense, so it's complete, there exists a forecaster who knows nothing about the true probabilities, who knows nothing about P star, and yet can pass the test with probability 1 minus epsilon. Okay, so that's like, whoa. It seems mind-boggling, and it is mind-boggling. And it's, I think, a really deep result. So we'll write down the theorem in a minute, but there are different interpretations of this result. So one interpretation is very pessimistic, and it's saying, no matter what test we try to formalize it, there are essentially knowledgeless fools who can pass our test, and there's no way to distinguish between someone who's a true expert and really knows the correct probabilities P star, and some charlatan who knows nothing and is just gaming the test. Okay, so that's a pessimistic interpretation of Sandroni result. I think I have a slightly different interpretation, which is there's really an algorithm. And the point is that if you work really hard and you observe, what's going on, what are the outcomes that are occurring or not occurring, and if there's something to be learned from this, if there's some method to the madness, then you can learn it by working hard and you can pass the test. And if there's no rhyme or reason to anything, then sure, we can't distinguish between a charlatan and a true expert, but what is a true expert anyway? There's no rhyme or reason. Every day is completely dissimilar from the one who came before it. So let's see the theorem, and then we can maybe ask questions about it or talk about it a little more. So just so we have it next to the definition of completeness. So this is due to Sandroni. And amazingly, you would think this is something that was known like in game theory from whatever, like the time of von Neumann, but it's not. It's from 2003. And it says that every test that is epsilon complete, so it's a minimal, seems like a minimal property that a test should have, right? A true expert will pass it with near certainty. Can also be passed with probability 1 minus epsilon by a forecaster who basically knows nothing. And who goes in not knowing anything about the true probabilities P star. Okay? So in other words, there exists a forecasting scheme, so an algorithm, that in every round just looks at the past predictions that it made and in the outcomes, so a single algorithm, such that for any sequence of outcomes or for any nature, P star producing the outcomes, the forecasts are accepted by the test with probability 1 minus epsilon at least. Yeah, so good. So I want to, since we have time, I want to say a word about, I won't be formal about the proof, I just want to give you a little bit of intuition about how one proves such a statement, and then we will return to the batch setting. So question about the setting, the theorem? Yep. So it's an algorithm that goes in not knowing anything. It has no inherent knowledge about these probabilities P star. So it's a single fixed algorithm. And whatever the P star is, it will be able to pass the test. Okay, so think about it like when we talked before about producing calibrated predictions. We know the test is going to be for calibration. So the forecaster does depend on the test. Okay, so I should say that, I should add that in my quantifiers. That's a good comment. Okay, so for every test that we fix, there exists a forecaster who can pass that test even though it knows nothing about the P star. There was another question? Yeah, is this connected to an experts type algorithm? It is connected, of course, so it's in the same setting, but to my understanding, at least at a superficial glance, we'll see there are also technical connections, but it's a different type of guarantee. So it isn't so much you're trying to compete with some external collection of experts, like you would in the experts literature, but rather it's sort of like, you're trying to satisfy calibration-like properties that are kind of more, some papers call these sort of like internal tests that are looking at kind of what's happening. You're not looking outside and comparing yourself to others, but rather you're looking inside at your own probabilities and seeing that they make sense. there are sort of unifying, technically, as far as I know, these are very recent, there are sort of unifying results kind of showing you can look at these sort of similarly. But yeah, it's not clear, at least a priori, that it's the same thing. Right? Different settings, Minimax theorems play a role, both for learning from experts or minimizing regret and here, but not exactly the same. There was another question here. I answered it. Okay, cool. Okay, so some intuition. I don't want to be technical about the proof, but I want to give intuition for how it works. And the proof is through the Minimax principle. So the way I want to do it is, if we talk about fixing P star, okay, the thing that is going to generate all of the outcomes in every round yi. And we could talk about adaptive P star, non-adaptive P star. Let's for now think about a non-adaptive P star, but things will work for an adaptive P star as well. And fix a forecasting scheme. So this is a rule for looking at the, what's happened so far and predicting a new probability for the current round. That's F. And let's call the score achieved by P star. So this is already hinting that we have some sort of game here, and one player is picking the P star, and the other player is trying to produce the forecasts. And let's say that the score is the probability that the forecaster passes the test. Okay, so the forecaster wants to have a high score, close to 1, and on the other side we have some nature that is trying to get the forecaster to fail the test. So the score is the probability that the test accepts. When the forecasts are being given, when the forecasts are being given by F, and the outcomes are being produced by P star. Okay. That's a number between 0 and 1. Okay. Then what do we know? Okay, so we know that the test is epsilon complete. Right? Or those are the kinds of tests that the theorem deals with. So what does that mean? It means that for every P star, no matter what P star is, if the probabilities are really predicted according to P star, then the test will pass with high probability. So in other words, for every P star, there exists a forecaster, namely P star itself, such that the score achieved when the outcomes are being generated by P star and the forecasts are being generated by F is at least 1 minus epsilon. Okay. So in particular, if we look at the worst possible P star in terms of kind of what score we can obtain when the outcomes are generated according to P star, and we sort of play the best possible forecasting scheme for that P star, the score we will achieve is at least 1 minus epsilon. So this is where I want to use a Minimax theorem. Some of you may not have seen these, but basically what they say is that when we have this kind of a game where the strategy is being played, we have two players. We have the nature player producing the outcomes, and we have the forecaster producing the forecasts. And they are both playing strategies that there are technical conditions, so the strategies need to come from a compact and convex set. So the strategies essentially we can think of as distributions over fixed deterministic strategies, and then, you know, the strategies are coming from a convex and compact set, technical condition. So I want to impress on you, I don't want to get into the technical conditions one by one and show that they're satisfied. I do want to impress on you that you can't always just use a minimax theorem whenever you want to. There are conditions that you need to satisfy. So in particular, for a game that's sort of a zero-sum game between two players, you can apply minimax theorems. And we have this score, and the score also needs to be convex concave in the first argument. In the second argument, it holds here. For zero-sum games, it always holds. Then the magic of the minimax theorem tells us that if we flip the order, we can obtain the same score. So there is a single strategy for the forecasting player that no matter what the nature player, the outcome player plays, will still achieve at least 1 minus epsilon. Okay? So the max over all the forecasting schemes. So there's just a single forecasting scheme, and I want to emphasize that it needs to be probabilistic. That's essential for using the minimax theorem. So kind of a distribution over deterministic forecasting schemes, such that even for the worst, so it's a single scheme, such that even for the worst possible P star for that scheme, the score we get is still at least 1 minus epsilon. So this is, I don't know what color to use, this is Minimax Theorem. And that is the forecasting scheme that we will play that is guaranteed by the theorem. Okay, so a single forecasting scheme. So what does this mean in words? There exists a forecasting scheme a single probabilistic forecasting scheme that for every P star makes the test accept with probability at least 1 minus epsilon. Okay. So just one remark, and this is going back to your question about soundness. So, you know, there's always a strategy for making the test accept. It is very potentially computationally expensive. Okay, so if I wanted to talk about strategies that are computable efficiently, it's unclear. And we can build examples where there does not exist such a strategy. And there's a couple of papers about it. I believe one by Fortnow and Vora, and one by Raphael Pass and others. I forget the names, their names. Good, and going back to what I said in the beginning, you know, you might look at this and sort of wail in despair and say there's no way to tell apart knowledgeable forecasters from ones that are just, you know, or I should say, this is sort of non-constructive, right? I'm just telling you that this exists. There are more constructive ways, there are more constructive algorithms for directly obtaining this forecasting scheme without just, you know, calling the minimax theorem as a black box, but they're still computationally intensive. And yeah, you might look at this and be depressed and there's no way to distinguish experts from charlatans. You know, another perspective is to say, yeah, if you observe, you know, very carefully what is happening, and there's some rhythm or some method to the madness, you can really capture what's going on pretty well using a learning algorithm. Good, so I think that's all I wanted to say about the online setting. Questions? Yeah. Could you repeat again? I had a hard time hearing.
So like even if the forecaster starts out knowing nothing and is a charlatan, is it not correct to say that over time he eventually sort of, not instead of passing the test in a fake way, just like actually learns to know what to do?
So the problem is that yes, if there is something to learn, it will learn them, but there might be nothing to learn, right? Like there might be the probabilities in every day might be totally unrelated to what's happened before, and still we can pass the test. So somehow the weakness of this notion of a complete test is that you really need to accept no matter what happens. Those are the kinds of tests we can fool. And maybe, we have tests that when there is some method to what's going on, they accept, but if not, they reject. Those will not necessarily be captured by the theorem.
If there's nothing going on, then the true forecaster also doesn't know what's going on. Is that correct?
So the question was whether the true forecaster doesn't know what's going on. So no. So maybe really, in every day, the true probability is some hugely complicated function, of, there's just like a fixed sequence of probabilities that we pick at random. No one knows what it is. And there's no way, given all the history, of knowing what the probability in the next day is. And still, we're able to sort of pass the test as well as that, as someone who does know the true probabilities.
In the definition of a test, is the length of the history fixed for a particular test, or the test is looking at histories of any finite?
Good. So I was thinking of it, just to make things a little bit easier, I was thinking of it as a fixed length. Everything we've said would holds for infinite sequences. And now you're asking about tests where they're kind of defined for any possible prefix, the outcome of the test. So I assume things would start holding after a sufficient number of periods have passed. So probably the probability of the completeness is a function of the number of days that have passed, and also your probability of fooling the tests would sort of approach 1 as more and more periods pass. Make sense? I mean, when we're talking about defining calibration tests, that makes sense no matter what the number of days we're talking about is, but even the true probabilities are not going to be calibrated until you've had a few days go by, right? Because if we're just looking at one day and really it was a 50% chance, we predicted 50%, the outcome is either 0 or 1, we're not calibrated yet. We need a few rounds to pass before things start making sense.
I have a feeling that there are some examples of situations where things are wildly miscalibrated on any finite prefix and yet in the limit they're calibrated. I'm not sure I'm remembering this correctly. It's in a paper by Shervish or a criticism of calibration as a condition that's written by Shervish in response to a paper by Philip David. So if you're interested, I can help you find it. And now that you've raised the question, I want to remind myself of what the reality is.
Good. Okay, so let us take our break and come back at 3:30. We'll talk about the batch setting again. We'll go back to the batch setting.